Welcome to the Challenges in Automotive Firmware Analysis webinar. My name is Eyal Traitel. Today I'm going to talk about automotive firmware analysis and the many challenges it provides to security analysts. I'm going to highlight some of these challenges, provide some tips on how to overcome them. I'll show some live demos, and overall, I believe this session will help both OEMs and suppliers, the security analyst community, with some tips on how to perform vulnerability assessments, firmware assessments in real life. A little bit about myself. I have over 25 years of experience in enterprise software. I worked in both large and small companies in a variety of roles. I'm working in Cybellum as VP Product Management since 2019. I'm responsible for product specifications, standards, regulations in the automotive market, and obviously working closely with our customer base on their projects. Favorite tools today: Google Sheets, Google Docs, and TCP, the Penetrace, and I'm old enough to still use VI. So for the younger guys, I'm sorry, I'm going to use some VI today. This is my email. If you have any questions, feel free to send those to me after the session. About Cybellum. So Cybellum helps OEMs and suppliers to develop and maintain secure connected components. And how do we do that? We provide a solution that helps both OEMs and suppliers to perform vulnerability management throughout the life cycle of product development, starting from the development phase, going up to the post-production phase, both in the firmware analysis part and the management of vulnerabilities that come out of it. We also provide solution for compliance with policies, standards, and regulations in a variety of ways, and we help customers to maintain security over the lifetime of the product after it is released to vehicles, using continuous monitoring and incident response capabilities that we have in our solution. So the agenda today is mostly focused on how to perform firmware analysis and the challenges that surround it. So let's dive right in. So why do people perform firmware analysis in the first place? They want to validate supply chain security because they don't have source code. There is a need to provide security over the development lifecycle. And the reason for the firmware analysis part is because the firmware is the final product, right? It covers all the assembled code, everything that comes out of the build process. So if you validate the firmware, you know that the product will be secure. If you validate any steps prior to that, it is good in terms of shift left methodology, but on the other hand, you're not sure you actually covered the actual thing that gets into the product, the actual software. And obviously compliance with the ISO and WP that basically talks about the need to perform vulnerability analysis and management throughout the life cycle. So basically what needs to be done at a high level: you need to detect and confirm the software bill of materials. You then detect vulnerabilities, and you also have to detect and confirm licenses for legal purposes. So the high-level challenges is, at the high level, it is not simple. You have to investigate firmware that in many cases, you don't have any prior notion of anything that's inside. You don't know the file formats, you don't know the file systems inside, the architectures, what are the applications inside, and what are their configurations. It's really a closed box that you get, and you need to investigate it. That's the common case. And existing solutions that are out there don't provide the complete picture. open source tools, there are so many of them, and each one covers a little part of the analysis, but not the entire puzzle. Commercial software is out there, and there are challenges there as well, because not always it covers all architectures and formats, and you still need to perform a lot of triaging of the results, because typically they don't contain context to the actual firmware, but they're more general related. And of course, lack of manpower and expertise. Investigating firmware requires a wide range of skills. It requires the understanding of the file systems and structures, and you need to understand what you are doing in the OS level. You have to understand vulnerabilities and the different technologies that they refer to, that they impact, and they vary a lot. And there are many mechanisms and operating systems that they impact. And maybe more than all the others, binary code analysis. So to investigate the actual executables require reverse engineering skills, which is very hard to find these days. The technical challenge, if you want to boil it down to one big challenge, is relevance. And what do I mean by relevance? Many of the results that are coming out of firmware analysis would be irrelevant, and they would be irrelevant to the component, the actual device, hardware, and its configuration, maybe vulnerabilities that only impact a certain CPU, and this physical device has another CPU. Vulnerabilities that impact other operating systems, not the one that is installed in the device, and so on. And many results are irrelevant to the firmware itself. File system, application configurations, maybe the vulnerable code is not in the binary, and so on. Services that are disabled. There could be many, many reasons. And understanding the relevance is a key part of what the analyst needs to do after he exposes all the potential findings, because many of them would be irrelevant. And the difficult part is how to understand what is relevant and what is not. So what is the firmware analysis methodology? You get a binary file, and you first have to identify the file formats, the inside structure of the firmware, and extract it. Once it is extracted, you have to identify the operating system and the configuration. You then identify all the other installed software and its configurations. You grab all the software licenses, you identify them if it's relevant and required for your analysis. You then look at other aspects of security, credentials, maybe firewall configuration, scripts that are inside the firmware, and so on. This could be a long list. And you then perform vulnerability analysis. You analyze the SBOM and the vulnerabilities. You then do the relevance investigation, and you identify further potential exploits, and perform binary code analysis if you have those skills available. So let's take a look at the real-life example. And we'll start with file extraction. So automotive firmware comes in many formats. It starts with compressed file formats and maybe IT image files like ISO and VMDK files, container image files, and so on. Sometimes it comes in other image types. WIC is just one example. And sometimes these are raw images coming from flash device dumps and so on. Just want to highlight that any of the formats on the slide could be hierarchically one inside another. So you could have a raw image file inside a zip file. And inside the dump itself, you might have some compressed files inside and so on. So the actual format may be a combination of formats in a tree of formats which you don't know upfront when you try to extract it. You can have different file systems, open source ones, the common ones in Linux. You sometimes, if it's a commercial OS firmware like QNX, you will have the QNX file systems and so on. So the list is long. Some vendors use some less common formats. Some names that come to mind: ODX, SREC, VBF, and obviously some vendors also use internally developed proprietary formats, and to extract those will typically require developing a custom extraction code unless you have the original utilities that would extract that. And the way to develop such extraction code would be by investigating hints from the binary data and understanding information, any information you might have on the format that you get from the supplier, for example. So how do you identify the file format? So files have file magic. You can identify them using the file command that covers quite a lot of known signatures. If it's one of the known formats, there's a lot of information on the web on file formats and file signatures, just highlighting two websites that cover some of these identifiers. Note that obviously the format at hand might be a different one, and the default magic library covers basic file types, and you can extend that and add your own MIME types to this database to cover more identifications. You can investigate the file using hex dump or strings commands to look at patterns in the file or any strings that might hint to the actual format. One of the questions for a given closed file would be, is the file or some parts of it compressed or encrypted? And the binwalk file extraction command with these options, with these arguments, could provide you some hints on whether the file has high or low entropy, which can basically hint to the fact of existence of compressed data inside or encrypted data inside. Why does it matter if something is encrypted or compressed? If it is encrypted and you don't have the decryption key, unlikely you will be easily decrypting and extracting that firmware. You'd have to go to the supplier to try to get the key from them. If it is compressed, that means if you're looking for other things inside, you will not see them because they will be in compressed format, so you will not see anything interesting in the strings output, for example. So how to extract? You can use tools like binwalk, PA tool, which is a generic compressed file format extractor, 7-zip. You can use the mount command in Linux that covers many image formats, and there are other tools available. And again, for proprietary extractions, you must develop your own extractor. So here, there's an example of binwalk. It takes a long time, that's why I'm not doing it live. This is of an AGL automotive grade Linux image. We are using the -e command. It is extracting the different structures of that image, anything that's inside. You can see that binwalk automatically identifies file systems. It identified an ext file system and it extracted it successfully. Here we are showing the extracted output. So what are challenges of file extraction? So I mentioned it earlier, recursion. So you need to extract recursively. So you can have images containing other images. You can have compressed files containing images containing other compressed files, and so on. So you have to extract to the lowest levels. And this is required to get to the actual files, the actual files that make up the OS. Symbolic files may cause issues with recursive extraction. You have to typically delete them before extraction, because you may have kind of infinite loops and so on. Duplication of data. Some firmwares come in these formats whereby you have the same firmware image for a device that is duplicated because it has a lot of revisions, and they are all aggregated into one big file. And basically all of these smaller images are actually the same content. And each of these independent partitions, they would have the same content, basically the same SBOM and so on. So there's causes confusion when you analyze it afterwards. File size. Some images, typically the ones I just mentioned, are very large, and some of the tools don't work as well on very large files, and you have to watch out for any hangs and so on. So once you have it extracted, you then perform the composition analysis, which is the SBOM detection. So you can do that manually by investigating strings, looking for key strings. In this case, for example, we are looking for the OS release file, which is commonly found in Linux operating systems and its derivatives. And you can see here that we identified the location of such a file, and the contents do provide details on the fact that it's AGL9. And now we know the firmware at hand is an AGL9, or very likely it is an AGL9 firmware. And we can obviously look up for additional information to validate our analysis. And how do we investigate further the rest of the components that are inside the software packages that are contained in the firmware? We can analyze the file system, look for locations like lib, user, lib, bin directories where all the executables and libraries are located, and we can go one by one and basically detect the packages that these libraries are part of, these executables are part of. Obviously, tedious work if the firmware is large, but this would provide us the complete picture. Obviously, it is not enough to detect the software component itself. We should also detect the version. This can be performed by searching for version strings, which are in many cases are out there inside the executable, or some unique source code strings that are compiled inside that are different between versions. This may lead to identification of specific versions. Sometimes it is in the file name. There can be many hints to that. Here we are providing some examples. We're looking at some strings that are coming out from an alza-lib library, and this is being taken out of a binary using some tools that we have, but it is possible to do that with extraction tools like strings and so on. And these strings can identify, as I mentioned, specific versions of the open source library that was the source for those compiled files. It's also possible to search for package manager configuration files like RPM and dpackage. You have the databases like the RPM packages database, which is in the varlib RPM. This can help you to identify things in a more structured way, because presumably this is a real-life distribution of Linux in which packages were installed using the official manners, using the official methods, and therefore the information will be right in the package manager configuration. It is possible to query the packages database like we are showing here, and then you just get the packages that were installed with their version information. And this could be a way to either trust that list or at least use that as a validation to the manual analysis. So it could complement the investigation or at least be the basis for the investigation. In some cases, I do want to note that it is misleading because the package was installed originally, but somebody stripped it out from the firmware manually using just RM commands. So the fact that it is in the package manager does not mean that it's necessarily inside the firmware. You have to validate that. Obviously, you can also search for ELF files for executables, investigate maybe there are some hidden ones buried inside other parts of the firmware. Also important to look into that as well using that angle. And you can also look at the dependencies of executables, which libraries they depend on, and this can also help you to traverse the executable path of the firmware and to investigate and identify all the other software packages, the libraries that are involved here. Just want to mention here that if you, this investigation is actually very important because if you miss an open source software or package, this will obviously cause you to misdetect vulnerabilities, misdetect software licenses, and this obviously you may miss a very critical vulnerability if you miss such a component. Nested detection, it is very important to understand that packages may contain other packages because they are compiled together. For example, zlib and OpenSSL are commonly located in other components. Here, for example, there is on the left side, there is a zlib that is detected inside the compilation of GDB. So basically, this file called GDB or GDB server, they contain both GDP, they are part of the GDP package, but they are also contained the zlib package as well. And it is important to identify that both are detected from that file. And this is important, again, also for vulnerabilities and for software licenses. Commercial software detection, this is obviously more tricky because you don't have the source code. You can look for vendor names, you can search in OPT directory, and just by knowing what is the component, you can also use some prior knowledge that, for example, in infotainment systems, you commonly see CarPlay or the equivalent Baidu CarLife. GraceNote is a very common library that is used in infotainment systems. So you can also use your know-how on what to look for, but basically there could be commercial software detection software packages that are inside the firmware, and you have to detect those as well. Not always they will have publicly known vulnerabilities, but they could be important for software analysis and also for binary code analysis that you may want to perform on these commercial applications. There are some open source frameworks that can be used for detection of software bill of materials. BAT is the binary analysis toolkit is a very common one. It is a tool that helps you to identify source files using identifiers that are unique. You have to build your own database using this framework. It is not so easy to use, and it is deprecated, so it's not a maintained project anymore. It is slow, it's not so easy to use, but just want to highlight that it is out there. Going now into licensing, there are various sources within files that may highlight the licenses that are in the firmware. You can look for names like notice or copyright or license txt and things like that. But once you have the SBOM, you can also use open source projects and open source Git sources and things like that to identify the licenses from with files named license or copying. or using the frameworks that I mentioned. So here, for example, we have the libpng. I'm searching in the main page for the word license, and you can see that there is a link to the license. If I go to look for curl, for example, when I go to the source code repository for curl, there's a file. First of all, GitHub automatically detects the location of license, but also you can see the copying file, which contains the license. Here I'm showing the contents of a file right from GitHub, looking at the actual file, at the actual license. Sorry. One way to investigate the terms of licenses, a common website is the enterprise-digicode.com licenses page. You can look for specific licenses and look at their license text and terms and so on. And there's also the SPDX license list, which contains a lot of the open source initiative licenses, and again, a way to investigate licenses and their terms. So just want to highlight, just want to show some small things. If I look at the libpng website, you can search for the word license. You can open the license, you can see the text and so on. If you copy the license name, you can search in the digicode website for that license, and in this case I found it, and I see it's a permissive license. That means it's free to use and share. And you can look at the license text and conditions and so on. If I look at the curl website, there's a copying file. Typically there's copying or license in big letter, capital letters, and you can actually look at the text and so on. Now let's get to vulnerability analysis. So again, how do you detect vulnerabilities? You match between SBOM and vulnerability databases like the NVD, the Japanese vulnerability nodes, or the Chinese vulnerability nodes. The thing is, the most important aspect is that you have to normalize the SBOM into standard package naming, and the main convention is the one that is used by NVD called CPE. For example, I identified that user bin PPPD file is identified as the PPP software, which is this website. But the question is, how is it represented in the vulnerability databases? So if you search for PPP and NVD, so I'm looking at the NVD website, I'm clicking on CPE search, and I'm searching for PPP. What you'll see is that you have many different names for PPP. There are many results. And how do you know which ones are the ones that represent the PPP that you are looking for? This is a challenge, because the feeds have inconsistencies. Human beings are the ones tagging the vulnerabilities in the packages, and in some cases they are over the years there's been different ways to tag the same actual package, and it might have been transformations that the open source project went through, different names, different owners, and so on. So here there's an example of many aliases that actually relate to the name PPP, and you have to match against all of them to identify whether those vulnerabilities make sense to the package at hand, to the executable at hand. Another challenge is that some feeds don't use CPE. They have like generic names. For example, here in the JVN you see point-2-point space protocol, and you have to basically match that against the CPE names to make sure this is the actual CPE that is referred to. Actually, the common just to highlight that the standard common versions of PPP, the right CPE for them is actually point-to-point protocol project point-to-point protocol, which is not necessarily the intuition that one might have. So you can search for the CPE. This is one of them, and then you can view the actual vulnerabilities for each of the versions and investigate whether they make sense, those version numbers make sense to the project, and so on. This is the most intuitive way to identify whether they are related or not. You can also use tools to perform CV search, not necessarily using the NVD. Typically, those tools like CV search will require you to build your own database, basically download the database update files that are available on the NVD website and then perform the search locally on your computer. But basically, the idea is the same. You have to know the CPE or investigate to get to the right CPE to have a correct match. So vulnerability triaging, as I mentioned in the beginning of the session, you have to investigate relevance. This is the most key part of the analysis, to understand whether vulnerabilities are relevant to the component and do they pose any risk. So that's the most important question. Is it relevant to my firmware? And if it is, does it pose a real risk to my firmware or to the component or the rest of the vehicle for that matter? So how do we investigate relevance? It's not an easy problem, but you would like to start with low-hanging fruits. For example, you would like to find easy ways to conclude that something is irrelevant. I mean, most likely, maybe not in all cases, but there's a good chance it is irrelevant. So why would that be? Because the version information in the vulnerability database is incomplete. Maybe the feature or the kernel module is disabled. Maybe the vulnerability, the vulnerable code is not in the binary itself. And then you'd have to do, if none of these helped you to conclude that it is irrelevant, you'd have to actually investigate the code itself and have a much deeper understanding to understand if it is still relevant or not. Just important to note, we see some customers that are saying, "Oh, it is in the firmware, but it is not used in a typical scenario, so it's okay. I can keep it." But this is crossing a general security practice, which is to remove unnecessary code or software, basically reduce the amount of software you have would always be considered a good security practice. So never assume that something will not be used by a hacker. So let me show you some real-life examples of vulnerability relevance investigation. So very common thing to see is that vulnerability information is missing a from. So it has a to, but not a from where it is vulnerable, from which release. For example, I'm taking a look at the Linux kernel CV here, CV 2020-10781, which is a Linux kernel CVE. You can see that it was found in a Linux kernel before 5.8 RC6, and it is in the kernel module called ZRAM. If I basically scroll down the page, I see that it is tagged as affecting any of the Linux kernel versions in the database, 3,000, 3,200 of those, up to excluding 5.8.0, in which the vulnerability was fixed because it was identified around that time frame where 5.8 was developed. So they fixed it in 5.8. However, nobody tagged the from version, and unless it was really introduced very close to the 5.8 development time, I mean, it is very unlikely that it affects all of the versions since 2.6. So how do you investigate? So in many vulnerabilities, typically the Linux kernel ones have a git commit link tied or mentioned in the NVD database, and you start investigating. You look at the commit link, and the kernel commits typically are very structured, and they are it is a very well-maintained project, obviously. And here, in this case, it is fully documented. What do I mean by that? So I'm looking at this commit. This is how I got to this page from the NVIDIA website. And they say that this commit is fixing this commit which introduced the problem. So now I have another commit number, which is the commit that actually introduced the issue. If I'm running a version that is not containing that commit, that means I'm not vulnerable to this vulnerability, by this vulnerability. So now I have this line, and I can search the Linux project. So I clone myself the Linux kernel source repository, and then I perform a search. And here I have a nice command called git tag, and this helps you to identify the tags, which is the real releases that contain that commit number. And here you can see that actually this CVE is only effective from 4.13 up to 5.8.0. So now I have to look back in my SBOM and see what is the Linux kernel version I'm using. In my demo here, it is focused on a single file where the kernel is 4.14. So 4.14 does have the issue, so it did not help me to identify in this case that it is irrelevant. But this is an example of how to investigate details beyond what is tagged by the original people that actually filed the CVE. They unfortunately did not include the from 4.13 information. So let's investigate further. And you can see here that ZRAM is a kernel module. And one thing I can investigate is the kernel configuration. In many cases, the firmware contains a Linux image that was compiled with the config flags. It is possible to compile with flags or without. If it is compiled with config flags, there's a script, you can Google it up, called extract ikconfig. It's part of the distribution of Linux, and it is possible to extract the config flags into a file, and you will see in this file whether a module is enabled or disabled in this compilation of the kernel, so you can easily see whether it has config ZRAM or does not have config ZRAM. And of course, you can investigate any of these on the internet to understand whether there is a config flag, and typically for modules there is, and if it is enabled or not in the kernel configuration file. Now I want to talk about optional code. So I'm going to investigate live a specific CVE. This CVE is called CVE 2014-9495. It's a libpng CVE, which we identified in real firmware. So I opened up front the details of that CVE. It is part of the libpng, which is a PNG image file support library. And you can see here, it's some buffer overflow in a function called PNG combined row. In the old versions of libpng, ones before 1.5 and 1.6.16, in which it was fixed, it is related to some PNG format called very wide interlaced or something like that. I don't have to know the full details of libpng to investigate. That's what I want to show. So I prepared up front a copy of the lib. I cloned the source code for libpng. So here I have my binary file, the one that was identified in the firmware, and I'm going inside the source code for libpng, and you can see that this is a tree of libpng. And now I'm just doing something very simple. I'm looking for the function name that is part of the vulnerability. You can see that this function name is basically declared or configured, actually included in the pngr util.c file, but it is used in pngread.c file. This is more interesting for me. So I'm going to actually just start looking for that function inside the pngread file. You can see here that this is only called if this flag is enabled. This is a C macro. So only if pngread interlacing supported is enabled, this code is compiled and calls the png combined row, because it's an optional part of the libpng library. So I'm going to copy that on my computer because I'll use that in a moment. So let me just continue traversing, looking for the other calls to png combined row. I see that I'm still in this section of that flag. There are a few cases here. This is another section. Notice that it's also only compiled if this libpng option is enabled. And I'm back here. Now let me go to the beginning of the file and search again for that feature flag. And I just want to take a look again at those parts. This is the part that I was already looking at. I'm just going until the end if. I'm searching, continuing my search. This is the second iteration. Again, a section. I was at here. I was looking at this section earlier. Now this is this part, getting to the end if. Now I'm searching for the third part. And here we see something interesting. So if this feature is enabled, right, again, I'm looking at this macro. If this is enabled, part of the code is a warning. It's a warning text. That means this string should be in the executable if the PNG read interlacing support is enabled. And if this PNG read interlacing supported flag is enabled, that means the PNG combined row might be called because it is compiled as well. That means if I see this string, that means my code is vulnerable to this vulnerability if this is a libpng version that does not have the fix. So let me copy that string. And now I can go in, go back. I can run the strings command on libpng, the libpng compiled version, and look for that string. And it is indeed there. That means that this binary is vulnerable by this CVE. If indeed it is running, it is a libpng of an older version. If it is a newer version, it is very likely that I have the fix and it is okay. I don't need to care about this CVE. So here you can see how you can investigate actually the open source to understand relevance or irrelevance of a vulnerability. Another thing you can investigate is mitigations. Executables offer mitigations to vulnerabilities such as Stack Overflow. There are many mitigations that are available in ELF files, Windows PE files. Executables also have similar protections. For example, if an executable is compiled with stack protection, it can be considered as a good enough mitigation to Stack Overflow vulnerabilities, which means if you identified an executable and you identified its version and you know it has multiple vulnerabilities, if the executable file has stack protection, you may consider that as good enough and mitigate it against those vulnerabilities, and these would then become also irrelevant vulnerabilities because it is much more difficult to trigger them in practice. There's a utility called hardening check. You can install that. It reads the ELF file and shows you easily in plain English whether you have any of these protections. Here it shows an executable, some executable object that I picked up, and you can see that it has stack protection. That means if I found any vulnerabilities on libgst code parsers, I can consider that as mitigated and irrelevant. More on this topic, we released a webinar a while back, also with ASRG, regarding vulnerability management and context-based analysis. I believe you'll find it useful as well. Just look it up and watch that as well. This is talk. Our team has been talking about context-based analysis more in depth than what I'm showing here, with more cool examples. So how do you fix vulnerabilities? You can obviously look for package upgrades, updated packages that fix a vulnerability, and also patch information that is available in the NVD database. So how do you identify patches? For example, TCP dump CVE 2016-7937. This CVE, when you search for it, only the links inside only provide high-level information. There's no links to patches. So how would you actually go and look for the actual patch? So one way you can do that is to clone the open source repository for TCP dump and then search in the Git log for a commit that may have the CV number. In this case, it was there. Note that in some cases, like here, you'd have to search for partial string, not the complete string, because it is not always as a straightforward search, not always trivial. Once you have the commit number, you can then use git show command to actually view the commit number or to browse directly to the patch in the open source repository website, like I'm doing here on the right side. And then you actually have the code of the patch. Now let's talk about penetration points. There can be many penetration possibilities to a device, to an ECU. And I'm going to talk about some of them just to give you some highlights. Unsafe credentials. There are many cases in which production ECUs have hard-coded credentials like admin and password. These are things that we get to see at Cybellum in real-life firmware. In some cases, there can be unsafe encoding of credentials. MD5 is, as you know, considered unsafe and can be easily cracked with tools like John the Ripper, basically to crack the MD5 into the original password. And in some cases, there are no passwords at all. We do see, in some cases, firmwares that have empty password for even the root user, like you can see in the following screen. So this kind of firmware if you try to log into it, you will not be asked for a password, and obviously this is a very high risk and very simple to use on the other hand. Very simple to identify from firmware. Just look for the password file and look up for this issue, search for this issue. Identifying services, you can analyze the systemd, for example, and understand its hierarchy to understand which services are configured to start a reboot and which ones are enabled. This can help to identify if some services are enabled, and obviously pose more risk when a component is really running. You can also look at open ports, search for firewall configuration files, search for their open ports, and identify things that are more risky when the firmware is actually booted. I'm listing here just examples of the Linux firewall configuration files and QNX configuration file. And public exploits. There are websites out there that and software that you can use to investigate public exploits for vulnerabilities. Such vulnerabilities would potentially be more risky than others because they have ready-to-use exploit code, and anybody on the internet can actually go in and look for these exploits, which could be a beginning of an entire penetration. Privacy, also of concern when you analyze firmware. There are various information pieces that can be leaked inside firmwares. I mentioned hard-coded passwords earlier, but you could also have project names, URLs, IPs that you may not want to expose, emails, phone numbers, social security numbers, and just an interesting website on the right side, regex, expression library website that can help you to come up with regular expressions that automatically detect these pieces of information when you search for them in a firmware. Databases can also be sources for information leakage, so it's interesting to look for them inside a firmware. SQLite is a common example for embedded software for flat file database. You can identify those files, search for them using their signatures, and you can read them using a graphical browser. Look for the information inside. There are freely available SQLite browser utilities out there. So to summarize, I've shown you today how firmware analysis is not a simple process, and that it has many steps and obstacles on the way. It is quite challenging. However, I do want to point out that it's recommended to focus on the low-hanging fruits first, the simple things that are easy to identify as also easy to fix vulnerabilities. First of all, the misconfigurations like no root password or hashed credentials that can be easily cracked, and focus on the most critical vulnerabilities. The Linux kernel vulnerabilities, for example, are good examples, and perform this relevance check that I mentioned to see what is relevant and what is not relevant for your firmware. And obviously a commercial option is always available, and we will be happy to discuss any of your challenges in firmware analysis. With that in mind, I'd like to thank you for listening. If you have any questions, you can post them on the YouTube comments, and also feel free to email me directly if you have any additional comments or questions to make. Thank you very much, and have a great rest of the day.